Greetings, this is Stephen McKenzie. If you want to learn more about me, I'll have some links in the description. And this is an overview of a project I've been working on that uses the CMSIS DSP libraries for embedded programming for microcontrollers. CMSIS stands for Cortex-M System Interface Standard, and DSP stands for Digital Signal Processing. FFT is a famous algorithm, the fast Fourier transfer. And this project features some sampling of analog data, voltage samplings off of the microprocessor, fed through the FFT for analysis and data visualization. So the purpose of this presentation is to provide a practical overview of how to implement a program that takes advantage of the library for analog to digital conversion and these mathematical library routines such as the FFT using the CMSIS DSP libraries. And so the focus is on demonstrating the tools in the libraries. And then I have a bibliography upcoming on the next slide to refer you to if you want to learn more about the algorithms themselves. Analog to digital conversion refers to the process of converting an analog signal, a continuous analog signal like voltage from a sensor, into a digital signal, a discrete digital signal that can be processed by a microcontroller system. And then at the highest level, the fast Fourier transform is a mathematical algorithm that converts a signal from its original domain, often time samplings, to a frequency domain. You think of like a sound wave. It's widely used for signal processing, including audio, communication, image analysis. It's ubiquitous. You couldn't use your phone without it. So here are the books I used to research this topic. Of course, I've been going through Introduction of Algorithms, again, by CLRS. That's Corman, Caesarson, Rives, and Stein. In particular, Chapter 13 on polynomials and the fast Fourier transfer. That's Chapter 30.1, Part 1 is the overview of the polynomial representation and coefficients and degree binding, uniqueness of interpolation, fast multiplication of polynomials. And then 30.2 is an introduction to complex roots of unity and the recursive approach to the fast Fourier transfer. And then there's Sedgwick, and this is only in this older book that I have on my shelf from 1992. It's Algorithms Using C++, and his newer books don't cover it. But if you can find that volume, you can refer to chapter 41, and it breaks down the topics nicely into categories of evaluating, multiplying, interpolation, and then as well as the recursion based on the complex roots of unity. Also, as a reference, I use The Art of Electronics by Horowitz and Hill. In particular, there's an appendix, a mathematical review. Also, Jonathan Valvano has the 3 volumes on embedded programming, and the first 40 pages is an electronic and digital logic overview. But for math, I have this really awesome college algebra book from 1947. And I don't know this for sure, but you could just imagine in 1947. So the author is Moses Richardson. He PhD, he was assistant, whatever, I forget what it was. He's assistant professor at the Brooklyn College, which it's where he taught. It was a hub for educating a large number of first-generation college students, many of whom were entering fields like engineering. And this would be right at the beginning, right during the Cold War, the early stages of the Cold War, the post-World War II era. where the United States experienced a major expansion in engineering and technological education. First, computers were coming out, and anyway, this book is very pedantic and structured, and it's very geared towards engineering and very applicable to that age. Just right on the verge of this huge scientific boom and the Cold War and so on. And so this book is kind of one-stop shopping for me. I don't really have to go anywhere else for most of my engineering math. Then, of course, I mentioned Embedded Systems by John Valvano. And then there's the online resources from ST Electronics, the hardware abstraction layer, the HAL framework, library framework, and also I mentioned the CMSIS. And then I'm using an STM32F4xx and the documentation that goes with that microcontroller. And also from Keil, they have some documentation, their ARM CMSIS pack with a test suite and so on. So we'll look at some code here in a minute. We're going to look at the ADC peripheral to convert analog voltage signals into digital values. And I'll give you a little demonstration on how the code is generated by the STM32F4xx, which is integrated with the IDEs from Keil UVision and also the STM32F4xx IDE. And we'll take a look at that and show you how they map directly to the settings inside of a GUI that give you a view of the pinout in the system. And then when you generate the code, you can see the one-to-one mapping. So we'll take a look at that. This is a view of the STM32F4xx graphical user interface for configuring your pins. Over here, the ones that are green, of course, configured and enabled. And then there's sort of a system view over here on the left. And ADC1 is a peripheral for the analog to digital converter. And the only, these settings here are the vrefint channel settings. And I pretty much have the defaults. I do have a clock prescaler changed to dividing by 2. Now, I didn't set it in here. I borrowed some code from another one of my projects, so I'm not going to generate code here, but I'm going to show you how you can set these up here and I'll show you the code that's generated. So we'll start from the main function. And of course, we initialize the hardware abstraction layer with the call to HAL init, and then the system clock is configured. And then I'm not using any GPIO right now, but I initialize it. But here I do have to initialize the ADC1. That is the peripheral that we're using. It's the analog to digital one. And then these are some functions some logic of the program. And this is the system clock config, which was generated by the STM32F4xx, which I did configure that, but we won't go over that now. Just we won't look at the UART, but I'll show you some of the results of it, because that is how I print the results, is through that peripheral. And so it's right here, MX ADC1 init. So the first thing we have to do is you have to not only set the clock speed for the entire board. It proliferates out through the system to where every peripheral has its own clock, and you have to make sure you initialize that, or you can't interact with it. And so these are the fields that we looked at inside the GUI. You see that it's programmatically set here by this generated code. And in particular, we set that ADC channel vrefint. And then we have these prescaler clock division by 2 and so on. So most of these settings are the defaults. So I do have a debugging session going on with the board is plugged in, the debugger is running. I'm using a terminal that I went to the Eclipse marketplace to get because it reads, it can be a serial terminal, and so you have to make sure that your baud rate matches what you've set up the device to communicate with, which is 115200. COM3 is where my ST-Link adapter is listening, is on COM3. Let me show you that real quick. So I'm running on Windows, and this is how you do it on Windows. You go to the device manager and you find you have to have the board plugged in, and you have ports, COM, and LPT, and here's this STM Microelectronics ST-Link virtual COM port. You get that open, you look at the port settings. So number one, it's COM3, it tells you in the title. And then here's the baud rate, and leave the bits at 8 bits, parity none, stop bits 1, flow control none. So that matches up with this terminal over here. And so what this code is doing, I have a test function called test FFT. It's going into a loop. That's the length of the buffer I've passed it. And it has a sequence of HAL ADC start with this global variable. It's a handle. And so it makes this call HAL ADC poll for conversion. And so it's getting voltage readings from the system, and it's converting it to digital and storing it into this buffer that is this length. And so you can see that I'm skipping my loop. My loop variable skips. It's plus equal 2, not plus equal 1. Because what we're doing is we're creating a buffer that's interleaved. We're creating a buffer of complex numbers. So the sample that we're getting from the voltage reading is our real number. And then we skip, and then we are putting a placeholder for the imaginary part of the complex number, just setting it to 0. So we're going to have this interleaved buffer of real numbers with imaginary numbers, but for now the imaginary number is set to 0 float. So I apologize for not making the output larger. I should have researched that before, but right now it just printed out the voltage samples. So it's printing it out though in a complex number format. So the left column we have the real number, and we have this floating point data, and then the imaginary part is zeroed out. Okay, and then we initialize the FFT algorithm with a length, what its expected length of the buffer. Then we go ahead and pass it in, and it does the operation. And then we print it. And so I've already stepped over that. And here are the results. And so now we have the converted results, that it's been converted from a time domain to a frequency domain. And now we're going to convert to magnitude conversion, which refers to calculating the magnitude or strength of each frequency. You take the square root of the sum of the squares, the real and imaginary parts of the complex number output. For more details on that, I'm going to refer you to CLRS algorithms or Sedgwick. And so we've done the conversion to magnitude, and we've printed those out. Now it goes back down to, it just keeps the strength. So it's not a complex number anymore. They're pure floating point numbers. And then we'll revisit I'm going to stop the demo now. We'll revisit the rest of the demo where the results are analyzed with a priority queue and a graph. We'll wrap that up at the end of the demo. For now, we'll get back to the slide presentation. So again, this fast Fourier transform is just one of several of the DSP library offerings. and that's what we'll cover in the next slide. It offers a rich collection of optimized digital signal processing algorithms for ARM Cortex-M processors, covering areas such as basic math, filtering, matrix operations, machine learning. So again, CMSIS stands for Cortex Microcontroller Software Interface Standard. It's a hardware abstraction layer for ARM Cortex-M processors designed to provide a standardized software interface for microcontrollers, making it easier to port code between the different Cortex-M based devices. DSP stands for Digital Signal Processing, which involves the manipulation of digital signals like audio, video, sensor data, using algorithms to improve or analyze that data. And then in this context, the DSP part of this library refers to optimized functions for performing digital signal processing tasks like filtering, transforms, and statistical calculations. And so here's some of those here on this slide. Basic math functions. I'm not going to read the slide to you. You can pause it and read it. But vector addition would be an example of that. Fast math functions. For example, fast approximation of square root. Complex math functions. Operations for complex numbers like the FFT. Filtering functions. Finite impulse response filter, which applies a weighted moving average to a signal, reducing noise. Another type of these processing algorithms. And matrix functions, matrix arithmetic, multiplication and manipulation. Transform functions like the FFT or DCT. DCT stands for discrete cosine transform. It's similar to the FFT, but it focuses on converting a signal into cosine components rather than sine and cosine components. It's widely used in JPEG and MPEG formats. Helps separate image or video data into different parts. In the context of the DSP library, DCT functions are used for tasks like data compression and signal processing. There's motor control functions in this library. There are statistical functions. There's vector copying, and they mean vector here. I looked it up. It is speaking of in a computer science definition of vector, not math or physics, but like an array type copies. Interpolation functions. SVM is a class we use to classify data points into categories by finding the optimal boundary. A hyperplane between them is an example of that. The Bayes classifier functions, like probabilistic classifier algorithms, distance functions, and calculating the distance between 2 points in different ways. Euclidean distance measures a straight line distance between 2 points in Euclidean space. Now Keil has some nice documentation on the CMSIS DSP. They distribute their software in what are called packs. If you use UVision, you'd be familiar with that. And they do have a test suite, which works best if you run it on Linux. It's CMake, uses pip, Python pip, and some of that framework. And so to print to that serial console, I use the universal asynchronous RT read transmit peripheral that communicates with the COM port on my PC on the host. And so there's a lot of material out there that shows you how to do that. And if you hit this sample, you should be all set up for it. You do have to provide an override of the syscall write and you replace the guts of it with a HAL UART transmit. But then you can use printf, as long as you also have your tooling set up. In your compiler options, you have to make sure that you're using, at least what I am using is hardware floating point. It's FPC4-D16. I'd go right to the settings, but I'd have to stop the debugging session. Maybe I'll do that. Let me finish the debugging session, then we'll go look at the settings of what you do to get the printing to work. Yeah, let's do that. So I have this priority queue written in C. That one of the nice features I have about it is it attaches to or detaches buffers. It doesn't have its own internal, so you can reuse buffers, which is a precious commodity in a confined, system like a microcontroller. And so I'm using, one nice thing is, now I do have a static heap allocator by Valvano, but it's even that's confining. I mean, your static memory is going to get fragmented. So I prefer to use algorithms that traditionally you would use dynamic allocation, but I make them array-based, fixed-sized array-based. And so one way to emulate a binary tree is to impose a tree semantic over an array. And so the canonical example of that is the heap sort or priority queue. And so you have contiguous memory of an array, and then you have index relationships, like your you find if you're element X, you find out your parent by the floor of X minus 1 divided by 2. Or if you're a left, element X wants to find its left, it's 2X plus 1, and right is 2X plus 2, and so on. And you build what's called a max heap. You have the max heap property, which I'm going to refer you to CLRS or any computer science book on how to implement the max heap and heapify function. There's some good MIT open courseware on it. But to build the heap, you start with the last non-leaf mode, which you determine by n being the length, how many elements are in the array, n divided by 2 minus 1. And so that positions you near the center of the array, but it's the lowest non-leaf mode, and everything underneath it is considered a leaf. And so you move backwards towards the root, calling the heapify function to ensure that every step along the way you're keeping this max heap property. And that simply is that the root of a subtree is greater than any of its child nodes. And so it's not like a sort where you have you don't end up with an actual sorted array, you maintain this heap property. Anyway, so that you have to do a swap, if your children are bigger than you and so on. And it's a recursive heapify function. And you keep hopping backwards until the largest element, if it's maximum heap, is sitting at the root, or the smallest if it's a minimum heap. And so anyway, I'm going to refer you to a book instead of me just kind of sloppily giving you a off-the-cuff description. But what's happening in the code is I'm going to attach to this, I'm attaching to the output buffer of the magnitude conversion, and then it is building the max heap, and then I will print it. And so you can see, I don't know if you can see it, it's small, but that index 0 is the root, and it has the largest floating point number. And you can see that you can't really look in sequence. You have to go through that algorithm of n divided by 2 minus 1, go to the last leaf, and that's how you have to calculate whether it is maintaining the max heap property. So then the next step I'm doing is to populate a graph. And so that each element of this max heap is going to represent a vertex in a graph. So there's going to be that number, which is 16. There are going to be 16 vertices in this graph. And so once we've created the vertices on the graph, then we're going to add edges. And the edges, the connections of the nodes, are going to be based off of peaks and valleys. So for each vertex in the graph, this code here, it compares the current value with the previous value and the next value, and it tries to detect a peak. And so if it detects a peak, then it edges are added between the peak and its neighboring valleys. So vertices before and after. So it's a bit of a toy, but you get the idea. It will show you peaks and valleys, and then after the edges are added, then we print out the adjacency lists. And one important thing about my adjacency lists are that they're not just an array of integers. They're 16-bit vector to save on space. So anyway, it's down here, and it's printed out in a grid, a 16 by 16 grid. And everywhere where there's a 1, there's a connection. That node is connected. Like vertex 3 is connected to node 5 and itself, and so on. So it prints out the graph. So that's pretty much the demo in terms of how the data structures are operate, and how all the data that I've pulled from the system is processed and reported upon. So as I promised, we're going back to the UART printing. And so here I am in the STM32F4xx. The way you get to this, by the way, if you're using the IDE, is to click on the .ioc button, and it brings this up. And you want to make sure that your code, you keep it in the blocks that are designated for you. Otherwise, if you generate code again, you might lose some of your work. So I'll show you that when we look at the code. But all the green buttons are enabled, and you can configure them over here. So I chose UART2, and so when I click on this, the mode comes up, and it's an asynchronous. The hardware flow control is disabled, and then the parameter settings for the GPIO settings are here. And I just have the defaults. Here's the parameter settings to make sure the baud rate matches my COM port. I showed you that earlier with the device manager. And then when you actually do go to using printf, make sure that your viewer, whether you're using terminal, or you can also use Valvano has a Texas, he calls it, that you can find up on his website as a COM port viewer. Or you can use PuTTY or your terminal emulators. But anyway, that's the main point, is getting the baud rate set. And then also you have to make sure you initialize the clock for it. So let's take a look at the code. So the first thing I do is I enable the peripheral clock. And then this instance of the handle to a UART number 2, that interface we were looking at inside the GUI. Here's the code it generates, and these are the properties that are being set on the fields of this UART2 structure. And so they map right up with what you set in the GUI, and the tool generates this code for you, so you don't have to remember it all. But I happened to grab this from another project that was working well with my system. But remember to set the clock, and then make sure your baud rates match is the biggest one, and make sure that your stop bits and your parity match up. Then also, if you want to use printf, I'll show you some things in the compiler settings to enable that, but you do have to overwrite the system call write with this function signature, and then with this call to HAL UART transmit. So printf diverts to this, and so printf takes care of all the format specifications and wraps up a buffer that it sends to this, and this actually does the printing, and the printf does the formatting for you. And so here I am in the compiler settings. Here I'm MCU, MPU settings. That you get to that through C build, and then settings. Number one, the CPU is going to be set. The floating point unit I have as FPv4-SPD16. I checked in the whole project, so you should get all of this if you're using my board. You might have to change it if you're not using my board. You have some other choices here. You can go none. Floating point ABI. I have it set for hardware, so that ends up being -mfloat equal ABI equal hardware. And then thumb2 instruction set. And then this is important. I'm using the reduce C library. That ends up to being the flag --specs equal nano.specs. Nano's the name of the minimal library, and so I have this checked. Use float with printf from the new lib-nano library, and that ends up being a -u underscore printf underscore float. And there's also a scanf where these port readers will take input from you with the scanf, which I haven't really ever tried that yet. So I do want to make some comments, because if you do download my code, if you're kind of uninitiated in embedded programming, you'll say, hey, this guy worked on the Microsoft Visual C++ team, and he's using all these global variables and so on. And yes, there's a lot of globals in embedded programming. That may seem counterintuitive if you've been drilled in your head not to use globals. But it's to manage the limited stack space in embedded systems. I did fudge my program a little bit, but things like buffers tend to be declared globally. Global buffers get loaded into SRAM, and you want to avoid stack overflow. Anyway, I'm not going to go through how the startup code works, but long story short is that there's no operating systems on these systems. It's just a firmware, and it runs from start to finish, and sometimes with a infinite loop, and so it just keeps going. But there's no hard drive. There are some operating system analogs you could make. There's a flash drive, but there's a known address in which the program gets loaded, and there's a linker file which describes the binary layout that's sitting on flash, and it all gets a lot of it gets loaded into RAM, SRAM. Some of the instructions are left on the flash, but the data gets loaded into SRAM, and so your global data stays in SRAM, and it stays in SRAM, and it doesn't contribute. If you're creating them on the stack there, you risk blowing your limited stack space for when you build a stack frame up from when you're calling a function. And so it benefits the SRAM's larger capacity than the stack, and prevents frequent allocation and deallocation, and makes it more stable for handling these relatively larger data sets. And so we're coming to a close here and wrapping up, but to recap, the key takeaways are: we have a program here that pulls voltage data. The program takes samples of voltage data from the analog to digital conversion and print them out as raw values. It interleaves that data for the preparation to feed the fast Fourier transfer. The real we interleave with zeros to represent the imaginary components to prepare for the input to the FFT, and then the FFT converts that raw voltage samples packaged as complex numbers from a time domain into a frequency domain, sort of revealing a sine wave components. And the frequency data, including the populated imaginary values, we print that out so you can see it. Then we calculate the magnitude after the FFT is finished, and that gets fed. Both the real and imaginary components are combined to compute the magnitude, the strength of each frequency. And this magnitude array is printed and then fed or attached to a priority queue, which populates based on the largest magnitude values. And then the queue is printed. Then we create a graph that takes that priority queue and initializes its internal data structure of vertices, an array of vertices. And then there's an edge assignment. The program creates a graph based on that magnitude data. It connects edges, connects the nodes based on identifying peaks and valleys, and the edge relationships based on the peaks and valleys of the magnitudes, representing those relationships of the different frequency components. And then that's the final report. The report is the graph is printed out into that two-dimensional, where you can see the peaks and valleys and how they're connected to which nodes. And then, this could be applied like in fault detection. By identifying peaks and valleys in a frequency domain, the program can highlight unusual frequency patterns that might indicate faults in a system, whether it's machinery or power system or sensors or whatever. And so that's it. I'll provide links to this project in my GitHub with these slides and with some links if you want to learn more about me and what's coming up next. Over the upcoming weeks, I hope to complete some other projects. I have a LCD screen attached to one of my controllers, and so use some of the libraries to interface with that. I have a Bluetooth device hooked to another, and so that'll be next in the queue. And then I have a Tiva Launchpad, a big one with the Ethernet. And so I'll want to work with the TivaWare low-level libraries there for raw sockets. I'm not quite sure what I want to do. I'm thinking about putting emitting packets with a custom protocol and then filter on those inside in Wireshark. I think that might be kind of cool. I'm not quite sure yet what I want to do with that, but that's an important project with me. And then I've downloaded some packages from ST. There's a TensorFlow, so I can get into some. I use TensorFlow a bit with Python, but I want to see what it looks like in the embedded world and maybe train some AI to read a bitmap with a circle or a letter on it, something simple like that. So those are all upcoming. So thanks for your attention, and you can contribute to the project if you want. It's under the GPL2. So thanks for your attention.